All right, let's get right into it. We're about to explore a pretty wild new idea in AI, and it comes from the very person who helped create the world we're living in today. This is a story about a king, its creator, and a potential revolution.
You know, when you think about modern AI, everything from recognizing your face in photos to the massive language models everyone's talking about, well, for decades, one single brilliant algorithm has been the engine driving all of it. It's been so successful, so dominant, it's basically the foundation the whole field is built on.
And that's where things get really interesting, right? Geoffrey Hinton, who is literally one of the godfathers of AI, helped invent this algorithm, and now he's publishing papers suggesting it might be a dead end. Why would you try to overthrow your own creation? That's the question we're going to unpack.
So first, let's properly introduce the reigning king. It's called backpropagation. And since the 80s, this is how deep neural networks have learned to do, well, pretty much everything. It's powerful, it's reliable, and you just can't argue with its success.
So how does it work, really? Well, think of it like learning to shoot hoops. You take a shot, that's what we call the forward pass. You watch it mess, and you see by how much. That's your error. Then you think backwards. Okay, I need to adjust my elbow, change my footing. You're correcting your technique based on the mistake. That's backpropagation. It learns by sending that error signal all the way back through its system.
This really breaks it down perfectly. It's a two-way street. Information goes forward to make a guess, and then the correction, the actual learning, comes all the way back. It needs both trips to work. It has to look forward, then stop, and then look all the way back. Now remember that detail, because it's going to be really important in a minute.
But here's the thing. For all its incredible success, Hinton now sees some major, fundamental problems with this whole approach. He's basically arguing that if we want to get to the next level, especially if we want AI that acts more like a real brain, backpropagation might actually be what's holding us back. So Hinton's case against his own masterpiece comes down to three big things. First, it's just not how our brains seem to work. There's zero evidence that our neurons are sending error signals backwards. Second, it's not great for learning in real time. Think about it. An AI processing a live video feed can't just hit pause on reality to run its backwards pass. And finally, it has to know exactly how it's built. If any part of the network is a mystery, a black box, the whole thing grinds to a halt because it has no idea how to send that error signal back through the unknown. Okay, so if the king has these cracks in its crown, what's the alternative? Well, Hinton is proposing something completely different, an idea that just gets rid of that backward pass altogether. He calls it the forward-forward algorithm. Now, the core idea here is a total shift in thinking. Instead of learning from an error, the network learns by comparing things. It still does two passes, but now they're both going forward. On one pass, it looks at real data. We'll call that positive data. On the other pass, it sees fake or negative data, and its only job, layer by layer, is to get really good at telling which is which. So, check this out. Instead of that one two-way street, we now have two separate one-way streets. On the positive pass, with the real stuff, every layer is trying to shout, "Yes, this looks right, high goodness score." But on the negative pass, with the fake stuff, it's trying to say, "Nope, this is garbage, low goodness score." It's a much more direct, more local way for each part of the network to learn. But hold on, you might be thinking, how do you make a deep network learn this way? Wouldn't the second layer just kind of cheat and look at the goodness score from the first layer? Well, this is where a really clever trick called layer normalization comes in. After each layer calculates its goodness, the output gets normalized. This basically erases the score itself, but keeps the underlying pattern. And that forces the next layer to find its own brand new patterns to tell the real from the fake. No cheating allowed.
All right, so all of this sounds super interesting on paper, but the big question is, does it actually work? Hinton's paper runs some early tests to see if this new kid on the block can even survive in the ring with the undisputed champ, backpropagation.
Let's look at the results. On the classic task of recognizing handwritten numbers, the MNS dataset, backpropagation gets a respectable 1.4% error rate. So what about the brand new forward-forward algorithm? It clocks in at 1.36%. For a first try, that's not just close, it's pretty much a tie. This proved the whole concept isn't just a fun idea, it's immediately competitive on a classic test. So what about something a little tougher, like the CFAR10 image dataset? Okay, here, backpropagation flexes its muscles a bit, getting a 37% test error. Forward-forward is a little behind at 41%, so yeah, the king is still on top, for now. But look at how close it is.
We're talking about an algorithm that's existed for a hot minute versus one that's been polished for 40 times years. Just being in the same ballpark is a huge deal.
And really, that's the main takeaway from these early experiments. The goal wasn't to dethrone backpropagation on day one. It was to prove that this idea is real, that it's worth our attention. And the results are clear. The forward-forward algorithm actually works.
So why should we care? If it's not blowing the old method out of the water right away, why all the excitement? Well, because the long-term possibilities of this new approach could completely change how we design, build, and even think about artificial intelligence.
And this is where things get really wild. First, like we said, it's a way more believable model for how our own brains might learn. Second, it's a perfect fit for new kinds of hardware, like tiny, ultra-low power analog chips that could run powerful AI on just a trickle of energy. And third, it opens the door to a truly mind-bending new philosophy of what computing even is.
Okay, brace yourself for this one. Hinton calls it mortal computation. Think about it. Right now, software is basically immortal. You can copy an AI model 1,000,000 times and run it on any identical machine. But with mortal computation, the knowledge is learned by that one specific chip, adapting to its own unique physical flaws and quirks. You can't copy it. When that piece of hardware dies, the knowledge dies with it.
Now, why in the world would we ever want that? Giving up the immortality of software seems insane. Well, the answer comes down to one word: energy. By letting each chip learn for itself, you don't need these perfectly manufactured, power-guzzling digital computers. You could use incredibly efficient, messy, low-power analog hardware instead. It's a massive trade-off. You lose the ability to copy, but you gain an unbelievable leap in efficiency.
And this quote from Hinton's paper just nails it. If we ever want to build AI models with 1 trillion parameters, something on the scale of a human brain, and have it run on just a few watts of power, this might be the only way to do it. The future of AI might just have to be mortal.
So we're left with this incredible, almost philosophical question. Maybe the path to smarter, more efficient, more brain-like AI requires us to let go of one of the most basic ideas in all of computing. The idea that knowledge can live forever, separate from the physical thing that holds it. It's a really deep thought, and it all started with just 2 simple forward passes.